Charles Darwin argued that organisms are not designed like ideal machines, but are assembled from pre-existing structures that have been modified over time. These imperfect designs are instead highly optimized for function. In trout, this principle is evident in the way that their bodies, muscles, and fins interact with flowing water. In streams, trout live in constantly moving fluid environments, where one day the stream can have high velocities and turbulent flows, and just a few weeks later, the stream can become slow and shallow, forcing trout to tuck into small pockets of reduced flow. Despite this, trout are able to move with remarkable efficiency. This is because trout are biomechanical systems shaped by evolution to minimize energy expenditure while maximizing their survival. My name is Pierce, and in this video I'll be examining how trout use biomechanics and fluid dynamics to maintain position, reduce drag, and optimize feeding in stream environments. To understand how trout achieve this efficiency, we can apply a central principle of biomechanics: structure fits function. In other words, specific anatomical features exist because they solve mechanical problems in the organism's environment. So, what are some of these anatomical features? Well, if you haven't noticed yet, trout have disproportionately large eyes. This is not just a random trait, it's a direct biomechanical and sensory adaptation to how trout feed in moving water. Trout primarily feed on very small prey, such as drifting nymphs and aquatic insects, which are often only a few millimeters in size and are carried unpredictably by the current. Rather than actively chasing prey, trout rely on a strategy known as drift feeding, where they remain relatively stationary and allow food to come to them. However, this feeding strategy presents a significant challenge. Light entering the water is constantly refracted at the surface, and turbulence further distorts the visual field, making it difficult to clearly resolve small, fast-moving objects. Larger eyes help solve this problem by increasing the amount of light that can enter the eye, improving visual sensitivity. They also enhance spatial resolution, allowing trout to detect small prey items against a complex and constantly shifting background. It's also important to recognize that streams are not always clear. After rainfall or seasonal changes, water can become muddy and highly turbid, significantly reducing visibility. In these conditions, light penetration decreases and visual contrast is reduced, making it even more difficult to detect prey. Larger eyes help compensate for this by maximizing light capture, allowing trout to continue detecting movement and contrast even in low visibility environments. From a biomechanical perspective, this enhanced vision directly reduces the need for unnecessary movement. This is critical because swimming in moving water is energetically expensive. By relying on visual detection rather than active pursuit, trout minimize energy expenditure while maximizing feeding efficiency. In other words, their large eyes allow them to convert a complex, often unpredictable environment into a controlled and efficient feeding system, demonstrating how structure fits function. So if vision helps trout detect prey, what other anatomical features shape the way they interact with moving water? One of the most important is fin placement. This is a clear example of the principle that structure fits function, where the location and orientation of each fin determines how forces are generated and controlled. In moving water, trout are constantly exposed to drag forces and turbulence, which can destabilize the body. To maintain position, these forces must be balanced without continuous, energy-intensive swimming. The caudal fin generates thrust when trout need to accelerate or reposition. The pectoral fins are critical for holding position, generating lift, and allowing precise control in the current. The dorsal fin provides stability by resisting rolling caused by uneven flow. Trout also have 3 secondary fins: the pelvic fin, the anal fin, and the adipose fin, which contribute to overall stability and control. Because of this placement, trout can distribute forces across their body and make constant micro-adjustments to maintain equilibrium. As a result, trout are able to remain stable in fast-moving water while minimizing energy expenditure, demonstrating how fin structure and placement are precisely adapted to the mechanical demands of their environment. To further understand how the structure of trout fit their function, let's take a closer look at their jaws. As mentioned earlier, trout's jaws are highly adapted for feeding, allowing them to rapidly open and generate suction to capture drifting prey with minimal movement, an efficient strategy in fast-moving water. However, in many male trout, the lower jaw develops a distinct hook shape known as a kype, particularly during spawning season. This structure is not used for feeding, instead it plays a role in reproduction. Male trout use the kype during spawning to compete with other males, helping establish dominance and increasing their chances of mating. This highlights how the same anatomical structure can serve entirely different functions depending on biological demands. To better understand how these biological adaptations connect to engineering principles and how studying systems like trout can inform real-world design, I spoke with a professional engineer and avid fisherman.
Hello everyone, my name is Lucas Folk. I'm a mechanical engineer. I graduated from Lafayette College in 2021. For a living, I design pumps and turbines for a variety of different industries, including the water, oil and gas, energy, and nuclear markets. I'm also an avid trout fly fisherman, and I spend a lot of my free time building, designing fly routes, and then utilizing them to test out new designs on the trout stream and observe trout in a variety of different settings. Something that I would use to analyze trout and how they interact with the stream that they live in. There's a couple of things. One, routinely we're conducting CFD or computational fluid dynamics analyses to understand what the flow path looks like through pumps. I think you could absolutely do the same thing for trout to understand how different shapes, how their fins interact, whether they are similar to airfoils for aerospace design engineering, or understanding what impacts their scales and the slime and the surface finish of the trout's skin kind of has in terms of drag and understanding that. So from my time spent on the water observing trout, I can say that, when we're talking about efficiency, you're talking about minimizing losses, and things that impact losses to a trout are, turbulent water or, fluid flow. So if there was a recent rain and the water is up, they're gonna, stay in the more calm sections. They're gonna hide behind a rock or a log in the water. On a hot summer day, the sun is heating up the water and it's taking the oxygen out of the water, which they need to conserve their energy and operate more efficiently. So they're going to be kind of either just sitting on the bottom of the stream where the coldest, most oxygenated water is, or more in the shade. So there's definitely some similarities between how I like to minimize losses in a piece of rotating equipment and how a trout interacts with its environment. So one historical piece of evidence for how pump design has influenced trout in the past is a couple years ago, back in the 1980s, the company that I work for was tasked with designing a pump to ensure for a hydroelectric power plant that the fish could safely go through the pump and be transported from the top side of the hydroelectric dam to the bottom side, or something similar. And so there were some regulations at that time for what the number of fish through the pump could be and how many fish must survive. Those regulations were dictated by the EPA and some other entities. Now, with constantly changing environmental impacts and numbers of trout declining, those regulations are getting more strict, specifically related to rotating equipment in rivers and streams. There's constantly changing regulations that dictate the equipment that I work on and how it's influenced trout from historical perspective, as time goes on, looking ahead at the future, I wouldn't be surprised if those regulations continue to get more and more strict for equipment manufacturers and manufacturing plants and things like that. When I look at trout, one thing that we've investigated that was directly related to trout and some other things is the surface texture of their skin. And there are a lot of animals, worlds, but specifically trout, that have a unique pattern to the way that their scales are formed. And we've actually investigated integrating designs that simulate either whether it's shark skin or the skin of a trout onto the veins and the hydraulic passageways of different impellers to reduce drag and minimize losses. So I definitely think that there are a lot of ways that and a lot of designs in the world that come from different animals, and I think that looking ahead at the future, we can definitely take inspiration from trout and their muscular structure, their skeletal structure, their skin, the slime that's on their skin, the size of their eyes in proportion to things, how well balanced they are, how the adipose fin prevents rolling and things like that. I think there are a lot of ways that trout can influence designs going forward.
As we have learned, trout are more than just fish navigating a stream. They are highly refined biomechanical systems shaped by evolution. Throughout this project, we've seen how structure fits function at every level, from eyes that improve prey detection, to fin placement that provides stability in current, to jaw structures adapted for both feeding and reproduction. Understanding these features requires both biological principles and mechanical concepts like drag, lift, and fluid flow. Researchers study these systems using engineering tools such as high-speed imaging and computational modeling, allowing us to better understand how trout interact with their environment. This topic also highlights a multidisciplinary approach, combining biology, engineering, and environmental science. Building on the ideas first explored by people like Charles Darwin, we can see that trout are not perfectly designed but are highly optimized for survival. Looking forward, these insights are not only influencing engineering design, but are also important for understanding how changing stream conditions may impact trout. Ultimately, trout do not fight their environment, they work with it, demonstrating how nature has already engineered efficient solutions to complex problems.